I think the most important thing I learned was you gotta get the metal that you're melting your solder to at the same temperature as the solder melts at. Otherwise, your solder will just become like a little bead on top of your parent metal and won't actually melt in, and you won't get a strong joint.
You gotta get the metal is heated up, or else the solder just melts, but it doesn't bond with the metal.
Mm-hmm. Nice. What's a way to tell if the solder didn't bond well? What does it look like?
Starts to bead up.
How about you, Hunter? What's the takeaway about soldering?
I think most important I learned was that you need the flux. I thought it was just the wire and the soldering thing.
Yeah, so the flux helps just everything melt together, and it helps clean everything before it melts. Nice. So here you can see the soldering tip right here is slightly dull looking. It's not terribly bright and shiny, but if I wipe it across the wet sponge, see, now it's nice and shiny and reflective. That's what you want the tip to look like when you're soldering. There are two methods you can use. I'll demonstrate both. The first method would be soldering just everything all at once. Clean the tip by wiping it on the wet sponge, then put a little bit of solder on the tip so it's nice, fresh, clean solder. Then I'm going to apply the soldering iron tip directly to the copper pad. Apply a little bit of solder to the iron to let it kind of help wick into the actual copper pad, and then touch the solder to the hot parts, not to the soldering iron tip. The idea is that you want the parts hot enough for the solder to melt. Otherwise you risk getting a cold joint if you're just always applying solder to the tip itself. Another method is tinning both parts first. That can be really handy if you're kind of juggling multiple parts, which, you know, you need to apply the soldering iron, the solder, and the wire. So technically, yeah, I can get my fingers to manipulate enough to do that, but it's way easier if I prepare all the surfaces first. So here I'm going to prepare this by what's called tinning it, which basically just means getting solder on it, pre-soldering the copper. So now there's a solder coating on that wire, and now I'm going to pre-tin the copper pad. Same deal. Get a little bit of solder on the tip, then heat the part, wait for it to heat up, then add some solder to the actual part that's hot, not necessarily only to the tip of the soldering iron. So it's not going to take much now just to heat up both and let the solders flow together into one mass. So now I apply the heat directly to the parts, let it all heat up. I moved it so now I'm touching both parts with the soldering iron. I let it heat up more, and then I take the tip away, let it cool down, and I've got another solidly soldered joint. Okay, so this is to show what happens when you have no restriction to the flow of current in a circuit. So here we have a voltage source. So we have the first item we need for a basic circuit. We have a voltage source. We have a path with the wire. So we have from positive goes through the switch, through this wire, and through this wire back to negative. So we have a path from positive to negative. It will be complete when we throw that switch. Then the path will be complete. So we have a voltage source, a path, and then the third thing is you need a load of some kind. This circuit has no load. There's no, well, this is kind of a load, but we'll see what happens with it. So you need something that is harder for the electricity to go through, so that it's restricted in some way, because if you have no restriction, then it'll just free flow as fast as it can. And electricity flows at almost the speed of light, so it flows really, really fast if you let it. So you do want to limit the flow. So now we're going to see what happens if we were just to connect a wire straight from positive to negative. I'm doing this setup so that the battery can be a little ways away from what is going to happen here, because the battery vents hydrogen when this happens. In fact, if our wire's long enough, I'm going to put it all the way down over here so it's well away. Okay, so are we ready to see what happens?
Yep.
When you have no restriction to the flow. Okay, go ahead and flip the switch. Ooh. So see how the wire got really, really hot, and in fact it's still really, really hot, and it, you know, burned smoke out. The insulation is all, you know, melted away, and I think it may have actually broken the connection somewhere. Oh, yep. See, we did break the connection. So there, the wire did disconnect there. That's why it didn't keep like burning and melting and stuff, because it actually fried itself. So this is like a fuse. It blew just like a fuse would. That's because we had no restriction to the flow. But if we hook a light bulb to this same setup, positive and negative, and this is a non-conductive piece of material, that's why it didn't just short across the table. So now if we flip the switch, Daniel, you want to flip the switch? So see, now it's, you know, okay, we're still flowing electricity, we still have a closed loop, but because we have a restriction here, it's not burning anything up, because that light bulb was designed to flow in a 12-volt circuit so many amps of current without burning up. So that's the difference between having a load, it's safe and it works and it provides a function, but if you have zero load, just zero restriction, then you end up burning up things. For measuring resistance with the digital voltmeter, you will set the dial to the ohms, the resistance range. That ohm symbol signifies that. And for general purpose use, you will usually start with the 200 scale setting and then work your way up as needed. So to test, to kind of calibrate your meter, you'll first just short the leads together and pinch them together as hard as you can. And you should, on these Harbor Freight meters, you typically can get it down to around 0.6 ohms. I've usually gotten it down to 0.5, 0.4-ish, and that is quote-unquote zero. If I use this resistor, this is just one resistor out of a bulk pack, and go just from one end of the resistor to the other, it says about 10.5, but remember, about 0.7 was our lowest, so give or take, it's a roughly 10 amp or a 10 ohm resistor, and that is correct with the stripes code that's on there. 10 ohm resistor. Okay, so here Taylor is measuring the resistance on this variable resistor. So what's that reading? Basically right around 14. Kind of, yeah, you have to push them on pretty hard there to make sure the connections are solid. So, and remember the zero on that meter is really right around that 0.5, 0.4. So it's about 13 ohms because we're in the 200 ohm setting. So about 13 ohms. So if we found a resistor, so what we did was we had this resistor, variable resistor in this circuit to see how much we would need to step down the 12 volt battery to light a little 3 volt light bulb. So now we learned that if we did around that was 13, right? Around a 13 ohm resistor, then that would work. Select the voltage range that you want to measure. You want it to be at or above the voltage you're wanting to measure. And then put the negative and positive leads on here. That battery it's actually a very good charge on there. It's measuring 13.13 basically, and you can see what happens if I hold these on here and then I switch this to the next higher setting. It's just less decimal points and it rounds it a little bit. to demonstrate measuring current or amperage. So instead of going here, which I would be for small currents, I'm gonna go here in the 10 amp range, and there's a fused connection in there. It says 10 amps max. There's a fuse inside that if you exceed 10 amps, it'll blow that fuse and protect the circuitry, or supposedly. I put an adjustable resistor here so that I can dial it in and show you the amperage flow, how much current will flow through the circuit through that load plus this load. And this goes from 0 to up to 25 ohms. So connect it, and as you can see, the light bulb is barely glowing. There's just enough circuit flow, current flow, to allow that filament to glow slightly at about 0.41 amps DC. I'm going to put an aluminum block under the resistor to help it stay cool, to help wick some heat away from it. So I'm going to slowly dial this up, and you'll see the current is increasing as I'm making this less and less of a resistance, and the light bulb is glowing more and more and more as more and more current flows through the circuit. So here we're at 0.62 amps, and we're glowing brighter and brighter. This is resisting less and less. And there I have zeroed out the resistor, so now this is no resistance practically. We're flowing the full current that light bulb will allow, and it's 0.93-ish amps DC.
And smile and wave. It's actually a video, so I'll just take a piece out of this.
Oh, you're just gonna take a
and turn it into a
snapshot.
photo.